Imagine you're an astronomer. You've spent years mapping a small patch of the sky, cataloging galaxies, measuring distances, building a picture of the universe one data point at a time. Then you look at a region roughly half the width of your outstretched fist against the night sky, and there is nothing there. Not a sparse scattering of galaxies, not a quiet neighborhood, nothing. A sphere of space so empty, so geometrically vast, that at first you assume the equipment has failed. You check your instruments. You recheck the data. You ask a colleague to look. They look, but still nothing. This is what Robert Kirshner and his team discovered in 1981. A region of the universe that contains, in 330 million light-years of space, roughly 60 galaxies. In a patch of comparable size anywhere else in the known universe, you would expect to find close to 2,000. That means the Boötes Supervoid, the structure we're going to spend the next 20 minutes understanding, is 97% emptier than it should be. That number is not a rounding error. It is not a gap in our data. It is not a known phenomenon with a clean explanation. The Boötes Supervoid is a hole in the cosmic fabric that physicists have been staring at for more than 40 years. And the most honest thing science can currently say about it is this: we don't fully understand why it exists. And yet, here it sits, unexplained, unmoved, and larger than anything our intuitions were built to handle. To understand why the Boötes Supervoid matters, you first need a picture of what the universe looks like at the largest scales. Not the scale of stars or even galaxies. Those are relatively intimate structures. The scale we're talking about is the kind that makes galaxies look like dust. When cosmologists map the universe in 3 dimensions, using the redshift of light from thousands and thousands of galaxies as a measure of distance, what they find is not a random scatter of matter. The universe is not like a fog or a uniform ocean. It is more like a big web. There are vast filaments, long braided structures of dark matter and gas, threaded with galaxies like water along a spider's silk. These filaments converge into enormous nodes, galaxy superclusters, some of the most massive gravitationally bound structures in existence. And between the filaments, between the nodes, there is something else. There are voids. Voids are the negative space of the universe. They are regions where matter decided, in the early universe, not to go. Or more accurately, regions from which matter was gravitationally pulled away, leaving behind something close to nothing. Not absolute vacuum, but profoundly, measurably underdense. Voids have less than 1/10 of the average matter density found anywhere else in the observable universe. They are not rare. In fact, voids account for roughly 80% of the observable universe by volume. Most of the space that exists, most of what is out there, is void space. The galaxies, the stars, the superclusters, the filaments that give us the impression of a full and rich cosmos, they occupy a thin, lacy shell around a vast interior of near nothing. Most voids are 30 to 300 million light-years across. They sit between the filaments like bubbles in a foam, bounded by galaxy walls, shaped by the same gravitational forces that built everything else. They are expected. They are predicted by our best models of how structure forms. They are, in the language of cosmology, normal. And then there is Boötes. The year was 1981. A team led by Harvard astronomer Robert Kirshner was conducting a redshift survey, essentially building a map of galaxies in a particular direction of the sky. The technique was methodical. They were measuring how fast distant objects were moving away from us, which translates directly into distance. Point by point, galaxy by galaxy, they were filling in the 3-dimensional structure of a small slice of the cosmos. What they found in the direction of the constellation Boötes, the celestial herdsman, was an absence so complete that it temporarily broke their understanding of what the universe was supposed to look like. The void they had stumbled into was roughly 330 million light-years in diameter. It was sitting approximately 700 million light-years from Earth, and it was, to a degree that strained credibility, fully empty. When Kirshner's team published their findings, the reaction from the broader astronomical community was cautious. Not disbelief exactly. The data was solid, but the kind of careful reserve that scientists adopt when a result seems to push against everything the prevailing model predicts. At the time, our understanding of how large cosmic structures could reasonably grow suggested that a void of that size was at the extreme limit of what was possible, perhaps beyond it. Here's the issue. The universe, at the largest scales, should be isotropic, meaning it should look roughly the same in every direction, statistically uniform across vast distances. This principle is called the cosmological principle, and it underpins almost everything we think we know about the large-scale structure of reality. A void of the size and emptiness of Boötes tests that principle. It is a structure so pronounced, so geometrically large, that its very existence asks a pointed question of our best models. How did it get this empty? The answer that emerged over the following decades was slowly, and with help. Let's take a moment and actually confront what 330 million light-years means. Not as an abstraction, but as a distance. 1 light-year is about 9.5 trillion kilometers. That is the distance light, traveling at nearly 300,000 kilometers per second, covers in an entire year. The Milky Way, our galaxy, our home, is roughly 100,000 light-years across. It took the light from the far edge of our own galaxy 100,000 years to reach the near edge. The Boötes Supervoid is 3,300 times wider than the Milky Way. If you were standing at one edge of the Boötes Supervoid and wanted to travel to the other side at the speed of light, the absolute speed limit of the universe, the fastest anything can ever move, the journey would take 330 million years. In that time, life on Earth went from the earliest complex multicellular organisms to everything that exists today. Every evolutionary branch, every extinction event, every single species that has ever lived or died on this planet would rise and fall during your crossing of the void. And when you arrived at the other side, you would find the first galaxies. Not a rich cluster, but a thin, strange tube of approximately 60 galaxies sitting in a cylindrical structure through the void's center, like a streak of gray through otherwise empty space. 60 galaxies across a distance that would swallow 3,000 Milky Ways. That is the scale of the problem. Now consider this. The Boötes Supervoid is not thought to be primordial. It didn't begin this empty. It was carved. The leading hypothesis is that the void formed through the coalescence of smaller voids over cosmic time. That 4 to 7 smaller voids, each themselves vast, gradually merged. Their intervening walls thinned and dissolved by the outward flow of matter towards surrounding filaments, until what remained was one enormous, near-spherical absence. This process is driven by the same force that built everything else, gravity. But in voids, gravity works in reverse. In dense regions, gravity pulls matter together, building filaments and clusters. In less dense regions, gravity causes matter to flee, to migrate outward toward the denser shells surrounding the void. The void becomes a region of gravitational repulsion, slowly, over billions of years, emptying itself further as matter drains toward the walls. Dark energy accelerates this. The universe's expansion, driven by whatever dark energy actually is, stretches the voids faster than matter can refill them. So, as the universe ages, voids grow larger and emptier. The Boötes Supervoid in this picture is simply an old void, a structure that has been draining for a very long time. That explanation sounds satisfying. It fits within our standard model of cosmology, and yet it doesn't entirely resolve the discomfort. Because even within that framework, the statistical probability of a void forming this large, this empty, in a universe shaped by the quantum fluctuations of the Big Bang, remains uncomfortably low. Not impossible, but the kind of result that makes physicists glance at each other across the seminar room. The current standard model of cosmology, lambda CDM, which stands for lambda cold dark matter, does technically accommodate the Boötes Supervoid. Its existence doesn't formally break the model. The simulations produce voids of similar size when you run them forward for billions of years. The mathematics permits it. But permitting something and comfortably predicting it are different things. What lambda CDM predicts is a universe whose matter distribution should be increasingly smooth the larger the scale you look at. At very large scales, the universe should look broadly the same everywhere, which is why the cosmological principle holds. The Boötes Supervoid is one of the places where that smoothing is most dramatically absent. It is a statistical outlier, not a violation exactly, but a stress test. Some researchers have pointed to the Boötes void as a possible probe of something more exotic: early dark energy, or warm dark matter, or primordial non-Gaussian fluctuations, deviations from the perfectly smooth early universe that would have seeded exceptionally deep underdense regions. If the early universe was not quite as uniform as we assume, the Boötes Supervoid could be a fossil of that irregularity, a scar left by physics we haven't fully characterized. The void also connects indirectly to one of modern cosmology's bigger problems. There is a tension, a genuine, unresolved tension, in our measurements of how fast the universe is expanding. Different methods give different answers, and the gap between them has been growing as measurements become more precise. The distribution and behavior of cosmic voids is one of the tools astronomers are using to probe this tension, because voids interact differently with dark energy depending on its nature. In other words, the Boötes Supervoid is not just a curiosity. It is useful. It is a natural laboratory, a vast, cold, empty space in which the behavior of the universe at its most extreme can be measured. Every galaxy that sits in or near that void, every photon that passes through it, carries information about the forces that shaped it. And there is one more thing the Boötes Supervoid does that is worth sitting with. When light from the cosmic microwave background, the afterglow of the Big Bang, the oldest light in the universe, passes through a supervoid, something happens. The photons lose energy. They enter a gravitational well, gain energy as they fall in. But because the universe is expanding, the well has become shallower by the time they climb out. The result is a cold spot, a ghost of the void, imprinted on the oldest light in the universe. This effect, the integrated Sachs-Wolf effect, has been detected. The cosmic microwave background has cold patches that correspond to known supervoids. Whether the Boötes void itself is responsible for one of those cold features is still being investigated. But the principle is clear. The void leaves a mark, even on ancient light. There are three questions about the Boötes supervoid that science genuinely cannot yet answer. The first is whether the void is truly as empty as we currently believe. Our galaxy surveys have limitations. The 60 galaxies we've identified are the galaxies bright enough and close enough to our detection threshold to register. There could be smaller, dimmer, more diffuse galaxies lurking in the void that we simply haven't seen. Or there might not be. The surveys are improving. Instruments like the Dark Energy Spectroscopic Instrument are mapping large-scale structure with unprecedented precision. But for now, the interior of the Boötes supervoid remains one of the least observationally constrained regions in the nearby universe. We are looking at it, and still not entirely sure what we're looking at. The second question is what happens inside a void over cosmic time. Voids don't just sit there. They evolve. As the universe expands and dark energy accelerates that expansion, large voids grow. They grow in size, and they grow in emptiness. The galaxies at the edges drain away. The interior becomes more rarefied. Cosmological simulations suggest that the largest voids in the far future of the universe will be staggering, structures that dwarf even Boötes. But the exact dynamics of what happens inside a large supervoid, how the remaining galaxies behave, how gas and dark matter are distributed in the interior, is still being worked out. The void is a dynamical system, and we are watching it mid-evolution. The third question is the one that carries the most philosophical weight. The Boötes Supervoid, Kirshner wrote after its discovery, was so unexpected that it forced astronomers to reconsider their intuitions about what the universe could look like. Is it alone? Are there other voids of comparable or greater size elsewhere in the observable universe, sitting quietly in directions we haven't yet surveyed with sufficient depth? Are there structures even larger, beyond our current observational reach, that would make Boötes look modest? The universe is 93 billion light-years across in terms of what we can observe. The Boötes Supervoid spans roughly 330 million of those light-years. There's a great deal of space in which very large, very empty things could be hiding. And we should remember, Boötes was found by accident. The Boötes Supervoid is 700 million light-years away. The light we use to see it left before complex life existed on this planet. By the time that light reached us, everything had changed, and yet the void itself had barely moved. It is ancient, patient, and vast in a way that the word vast can't quite hold. There is a temptation, when confronting objects like this, to reach for the sublime and stop there, to let the numbers wash over you and call it wonder. But the Boötes Supervoid asks more than that. It asks why there? Why that size? Why that empty? And the fact that 4 decades of modern cosmology, with redshift surveys and dark matter simulations and space telescopes and petabytes of data, have produced an answer that amounts to probably just gravity, but we're not entirely certain, tells you something real about the frontier we're standing at. The universe is not obligated to be comprehensible. It isn't designed to make sense at scales we were never built to perceive. And yet, the fact that we have perceived the Boötes Supervoid, that a handful of humans in the 1980s pointed telescopes at a patch of sky and noticed that something was missing, is, in its own way, the more remarkable fact. We find the absences. We name them. And then we spend decades arguing about what they mean. Here's the question that stays with me. If the Boötes Supervoid formed through the merger of smaller voids, if it was assembled piece by piece over billions of years of cosmic drainage, then we are looking at it mid-process. It is still growing, still emptying, still draining matter toward its edges, in a universe that will continue expanding for hundreds of billions, perhaps trillions of years. How large does it get?